Introductions. Chi-square application is a common non-parametric statistical test. These statistical tests follow a specific distribution known as chi-square distributions. In general, the tests we use to measure the difference between what is observed and expected according to an assumed hypothesis.
The chi-square distribution has shown the following characteristic that we can see from the diagram. It is positively skewed. However, as the degree of freedom increases, the curve approaches normal. Chi-square values are never negative. This is because the difference between the observed frequency and the expected frequency are powered by square. There is a family of chi-square distribution. It is based on degree of freedom. The number of degrees of freedom are determined by k-1, where k is the number of categories. Therefore, degree of freedom determines which curve to use. When the degree of freedom changes, a new distribution are created.
There are three applications of chi-square test. First is goodness of fit of distribution. This application distributes into two, that is equal and unequal expected frequency. Second is conduct a test of hypothesis to verify that data grouped into a frequency distribution is a sample from a normal population. Last is determine whether two classification criteria are related, is known as contingency table analysis.
Test 1. The goodness of fit test is one of the most commonly used statistical tests. The purpose is to compare an observed distribution to an expected distribution. Let FO and FE be the observed and expected frequency respectively. Commonly, the question will be asking, is the difference between the observed value and the expected value due to chance, which is sampling error? FO same with FE. Inversely, not due to chance. FO not same with FE. The illustration of this test involves the case in which the expected cell frequencies are equal. The first step in conducting the significant test is to compute that there is no difference between FO and FE in null hypothesis, while there is a difference between FO and FE in alternative hypothesis. Second step is the significant level equal to 0.05 as stated in the problem. The third step is select the test statistic, chi-square distribution. Calculate chi-square using the formula. Step 4. Formulate the decision rules. The decision rules in hypothesis testing requires finding a number that separates the region where we do not reject HO from the region of rejection. The number is called critical value. The critical value is chi-square with k-1 degree of freedom, where k is the number of categories. Since there are 4 categories, so 4 minus 1 equal to 3 degrees of freedom. The critical value for 3 degrees of freedom and the 0.05 level of the significance is found in Appendix B.3 table. A portion of that table is shown in the diagrams. The critical value is 11.07, located at 3 degrees of freedom and the column of 0.05. If the computed value chi-square is greater than the critical value, then reject the null hypothesis of no difference between FO and FE results. Step 5. Compute the value of chi-square and make a decision. The calculation for chi-square reported in the table. Column 1. Determine the difference between each FO and FE. The sum of these difference always equal to 0. Column 2. Square the difference between each observed and expected frequency. Column 3. Divide the result for each observation by the expected frequency. Finally, total up this value. The result 2.2 is the value of the chi-square. The diagram chi-square probability distribution for 3 degrees of freedom, showing the region of rejection, 0.05 level of significance.
Goodness of fit test. Unequal aspect frequency. Step 1. State the null hypothesis and the alternate hypothesis. H0 is equal to there is no difference between F0 and Fe. H1 is equal to there is a difference between F0 and Fe. Step 2. Select the level of significance. In this case, the level of significance we use is 0.05 as stated in the problem. Step 3. Select the test statistic. The test statistic we use is chi-square distributions. Following is the formula of chi-square distributions. Step 4. Formulate the decision rule. Reject H0 if chi-square value greater than the critical value. In this case, we know that the number of category is 4. After we let into the formula of critical value, we get x squared 0.05 and the degree of freedom is 3. Refer to the chi-square table, we know that the critical value is 7.815. Now, we need to find the expected frequency. In this case, we know that the frequency observed sample is 150 Barton residents. The expected frequency is computed by AHAA% times with 150 in every number of time emitted. The table below is the calculation of the expected frequency. Step 5. Compute the value of chi-square statistic and make a decision. First of all, we need to find F0 minus Fe for every number of time emitted and square the answer divided by Fe. After that, we total all the answer and get the chi-square value is 1.3723. In conclusion, the computed x squared of 1.3723 is in the do not reject H0 region. The difference between the observed and the expected frequency is due to change. We conclude that there is no evidence of a difference between the local and national experience for hospital admissions.
Test 2 is testing the hypothesis that a distribution of data is from a normal population. Step 1. Calculate the probability for each class. Convert each class limit into a z-score using the mean and standard deviation are given, then find the probability. We using the area under the normal curve table to find out the value of areas and calculate the z-score. Step 2. Use this probability to compute the expected frequency for each class. Step 3. Select the test statistic. The test statistic follow the chi-square distribution. Step 4. Compare the compute statistic to the critical statistic and make a statistical conclusion.
Test 3. Contingency table analysis. Contingency table analysis is to investigate whether two traits or characteristics are related. In this analysis, the degree of freedom is equal to number of row minus 1 times with number of column minus 1. Example, the Quality Control Department and Food Town Incorporated, a grocery chain in upstate New York, conduct a monthly check on comparison of scattered price to processed price. The chart below summarizes the result of a sample of 500 items last month. Company management would like to know whether there is any relationship between error rate on regularly priced item and specially priced item. Use the 0.01 significant level. Step 1. State the null hypothesis and alternate hypothesis. H0 is equal to no relationship between error rate and item type. H1 is equal to there is a relationship between error rate and item type. Step 2. Select the level of significance. 0.01 as selected in this problem. Step 3. Select the test statistic. The test statistic follow the chi-square distributions decided as x squared. Following is the formula of chi-square test statistic. Step 4. Formulate the decision rule. Reject H0 if chi-square value greater than critical value. In this problem, we have 3 rows and 2 columns. After let into the formula of critical value, we get x squared, 0.01 and 2. and refer to the table of critical value of chi-square. The critical value we get is 9.210. Step 5. Compute the value of chi-square statistic and make a decision. First of all, we need to find the expected frequency. Expected frequency is calculated by using formula row total times column total and divide by grand total. After we get all the expected frequency, we start to compute the chi-square statistic. To compute the chi-square statistics, we use the formula sum of FO minus FE square divided by FE. So, in this case, the chi-square value we get is 8.033. In conclusion, the computed x-square of 8.033 in the do not rejection HO regions. The null hypothesis is not rejected at the 0.01 significant level. So, we conclude that there is no relationship between error rate on regularly priced items and specially priced items.
Conclusion: Non-parametric method of chi-square application have three types of application. They are goodness of fit test, testing the hypothesis that a distribution of data is from a normal population, and contingency table analysis. We use it for data measure with a nominal scale.